is very important for quantum information. And then we'll have the post-lab feedback as with last week. And that will be through a poll here, not on Canvas. So we're gonna be doing a bit of both. Just to review the ground rules, we want to make sure that everyone feels like they can speak and ask questions in this. We want it to be very open and friendly for everyone. So please don't spam the chat or put answers to problems in the chat unless you're asked. Keep your questions relevant to the topics being discussed. And if you have any off-topic questions, you can ask them on Piazza if they are content related, or Discord for logistics. And then we haven't done any raising of hands, but if we move into that, that is an option for the future, I guess. Okay, and then just to reiterate, we want to make sure that everyone has ample opportunity to speak. So please don't ask questions or answer questions like too consistently, I guess. If you tend to answer a lot, like make sure that other people have an opportunity to speak, because the chat does fill up very quickly. And please, if you don't answer questions a lot, please do. There's really no consequences, even if something's wrong or if you think your question isn't a good one. A lot of times questions that sound kind of stupid like are actually very important and nuanced, and people that already understand something might not even think of it that way because you're too used to it. So with that, do we want to do the feedback now on Canvas?
Yeah, we can do that.
Okay.
Hey everyone, super happy to see you again. No one got scared away. I am going to share my screen. You're going to see all my Discord and everything, probably the same way your screen looks. Okay, so hopefully you can see a video, is that right? All right, so like Sarah already mentioned and like we talked about last week, we are introducing attendance points this week. This is 40% of your grade, but we'll make sure everyone gets the points that they've earned. And we understand that everyone's still getting warmed up to the course, and so don't worry, we'll work with you. I just want to pause and have us watch this quick video. Ooh, that's already playing. Which is one of our staff members walking through just really quickly how you set up your Canvas account if you haven't already, and then how you take the attendance quiz that we're about to pause to take. So I will play that.
It's a bit quiet.
Is also listed on the Q by Q Canvas instructional guide. You'll find a walkthrough of how to set up your account here. So you want to log in with the email that you provided to Qubit by Qubit on your application. And then if you have not done so already, please hit forgot password as instructed in the instructional guide in order to get a reset link sent to your account here. If you have any problems logging in or you're unable to do so, if you go to the frequently asked questions on the Canvas guide, there's a form here that you can submit a help request. So I've already done that and set everything up, so I'm going to go ahead and log in. This is what your dashboard should look like once you're in. So I have a course. And then this is what your view should be. In order to access your attendance quizzes, you'll want to go to quizzes. In here, I can also see the section that I'm in. So I am enrolled in Lab 1B. Unfortunately, I missed this quiz this morning, so I will be unable to enter in any information. The quiz will close within 20 minutes of your lab session starting. So click on, just for this example, I've created an additional quiz. Normally all attendance quizzes are found under surveys. So go to example quiz. And here are the instructions. So you're going to make sure to log into Canvas 48 hours before your lab session to make sure your information is correct, and then 5 minutes before your lab session to give Canvas time to load your quiz. So again, this attendance quiz will be due within 20 minutes of your lab section, so you'll see there's a limited time that you're able to submit this quiz, so make sure to submit it within that window. And then you will be given a unique access code at the beginning of your lab session to take the quiz. This is unique again to every lab section, so make sure that you're paying attention to your lab TA and the moderator. They'll share this access code with you. I was already given my access code. And then again, I can see the instructions, and then I select my answer to this question. So I'll say that I understood this week's content quite well, so I'll give myself a 4. And you'll be able to see that your response is recorded, but you won't get a correct answer. You should be unable to view a correct answer as it's a survey. So as long as you have a submission from you, then your answer is correct. If you have any questions, make sure you check out the Qubit.
Okay, hopefully that's pretty self-explanatory. I will, if I can stop sharing screen, I will give you all your passcode. I will also, just a few other things, I'll give you the access code for this week's quiz. I will drop in the chat the Canvas guide that is already made available in Discord. And then also, for students who have not had a chance to set up Canvas yet, we know you're a Tuesday lab, so it's fairly early in the week, and some of this information just went out. I'm going to drop an alternative form that you can fill out if you haven't set up Canvas, so we can make sure that we get your attendance logged. So just quickly, Sarah, maybe if we can take 2 minutes, and then I'm so sorry, I'll let you get on with things. If people can pull up their Canvas account, the access code is 1139. I will drop it in the chat. And you can log into Canvas and take that quiz. And I just dropped in the chat if the form to fill out if you don't have Canvas set up yet.
And I see a question from Diana about whether it's asking how well you understood the material with regard to quantum gates, with regard to trigonometry. I believe it's just the section as a whole, although the quantum gates are meant to be pretty high level, so you shouldn't expect to understand it in depth. That's all correct. Rachel?
Is that the non-graded quiz?
Yes.
Okay, thank you.
Which lab day is this?
This is lab 3 on Tuesdays from 8 to 9 p.m. If you're in the wrong lab, like if it says that you're in a different section, you can fill out this troubleshooting form that I will also drop. Patrick passed the non-graded quiz, which is awesome. I'm glad some people are finding it. Okay, I will let Sarah carry on. Feel free to finish that. For this week, it will be open more than the first 20 minutes. It'll be open for the first hour for the full lab, so you can get comfortable and submit it as soon as you're able to. All right, all done, Sarah.
Great. So first thing we're going to go into are a couple common questions we had from last week. So the first one is on combinations of logic expressions. So how you might represent something like, I guess, this expression here. So I'm just going to draw this out and let me know if it's at all unclear. So we have A, B, and C as our inputs, and we're bringing A and B to a NAND gate, which hopefully you guys remember from last week. And then this output then goes to an exclusive OR gate here. And to give a brief example, I don't want to write out the full truth table as it does have 8 entries, but it's pretty straightforward to extend. If we put a 0 and a 1 on inputs A and B, and then maybe put a 1 on input C, we have our A and B go through a NAND. So this, remember the NAND requires, or actually I guess if someone wants to put in the chat, what does a NAND do? What would you describe it as in English? Not and, yeah, pretty much. So like if you have a 1 on A and a 1 on B, then you have A and B. But because this inverts it, that's actually the only only pairs of inputs that will give you a 0 out of this NAND. So here we have a 0 and a 1. So that gives us a 1 out because we don't have A and B. So then we have C coming in with just a 1 because it hasn't gone through anything. And this is going into an exclusive OR. So an exclusive OR is, like we said last week, an English OR. If you have a 1 and a 1, you don't have either input. I guess we're going to call this input like X at this point. We don't have X or C. We actually only have both of them. So this will give us a 0. And you can progress through any logic gate similarly to that. Are there any more questions on logic expressions similar to this? And did that make sense to everyone? Got a very good question from Thomas. Why are there 8 options? It's because we have 3 bits here. And so each bit can be represented by a 0 or a 1, like we said. So that is 2 options. Like we said in base 2, we have 2. If we have 3 bits, we have 2 to the 3 possible inputs, which is 8. So I've got a question on recursive inputs. I'm not totally clear what you mean by recursive inputs, Benjamin. So if you could clarify, like going backwards, like here? I don't know. From Kevin, I have a question on if there are no parentheses. That isn't super well defined. That is a very good question. I would assume left to right, but it's not necessarily, like you don't necessarily know what someone meant by it. There's not a super standardized convention for it. We had a discussion about this actually in our TA meeting, and it's not, the default assumption should be go left to right if there aren't any parentheses. Okay. Benjamin, this is a little bit more complicated than what we have time for in this class. Please ask it on Piazza and I can give you a more detailed answer. Yeah, okay, so with that, I'm gonna move on from the logic expressions, and we have a question on logic gates that was very commonly asked as far as what these gates are actually made of. And we have a written out answer with a transistor. This is often represented like this. This is a MOSFET, which stands for metal oxide semiconductor field effect transistor. And this here is often called a gate. This is a source. This is a drain. None of this really matters. That's just what they look like. A lot of times you'll see representations of these same logic gates, but with multiple of these transistors to describe what one of those logic gates is. And so this does not like directly map to any of the gates that we discussed. It depends all how you hook it up, and normally you use more than one. So you can also have one like looks like this. And I just want to, I think it's a fun question. Here, can you guys guess what a transistor looks like? This is still a MOSFET, but can you guess what the difference between these two is? And the secret is this guy. Yes, Benjamin's correct. It is it's functionally an inverted version of this. It's not, and I guess it is literally an inverted input. So this is often called a p-type FET, which just means that you have positive charges being accumulated. So you want to have the reverse of your voltage here. Well, this is an n-type FET. And so you often will represent these logic circuits with both n-type and p-type FETs, which is pretty fun. So yeah, these circles are like very, very important. Like they're always just a knot of what's happening. So you will see them everywhere. Okay, so now we're going to move on to the actual content for lab 2, unless there's any other questions on the material from last week. I guess I'll, if you guys have more questions about transistors and cells or binary arithmetic. Yeah, so Benjamin, you are correct that the difference, this p-type and n-type means that your depletion rate, it's a bit complicated, but the charges that you have or the charge carriers that you have going through this can either be electrons or holes. So when electrons carry a negative charge, while a hole carries a positive charge. And so p-type is hole dominated, while n-type is electron dominated. And that is why there is a difference between the operation of these two. And so you want to have the opposite potential applied on the gate. So this is just the voltage. This is also a gate, but you apply a voltage here, and you want to have a negative voltage here and a positive voltage here. This is more complicated, so don't worry too much about anything. The only real important part is just that these are just kind of like a brief overview of what this actually looks like. And this is a very complicated field that you can go in depth in for years. And I did that and then I forgot all of it. So this is what I remember, and that's what I'm going to tell you guys. But yeah, don't worry too much about it. Yeah, if you ever see these symbols, that's what these mean. And then, okay, I'm gonna take one more question. And then you have a lot of questions, which I appreciate, but we want to go too in depth. So I think it is a very interesting idea about how they make all these components. So all these components are very, very small. And what they use to create these components and these wires is something called lithography, or often photolithography, where you have some material that reacts when exposed to light, kind of like how you might tan in the sun. These materials will react and get softer when they're exposed to light. And then you can put like an acid on them to remove the parts that have been made softer, but the parts that have not been made softer will not be removed. And in this way, you can make shapes all the way down to the size of the wavelength of light, or the wavelength over 2. So you can easily get down to, I guess, hundreds of nanometers with this method. And then for even smaller, you can use electrons instead of light. Okay, so I'm going to move on from last week's questions and go into our learning objectives for lab 2. So the 3 sections for this lab are going to be basic trigonometric functions at different angles, coordinate systems, and then summation notation, which we'll just very briefly go over at the end. So the trigonometric functions you may have seen previously are the sine, the cosine, tangent, and there's inverse versions of all of these. The cotangent, secant and the other one, they're just 1 over the cosecant. They're just 1 over the sine, cosine, and tangent. So we're not really covering those. But all of these are defined generally by the unit circle. So each location on the circle corresponds to some value for the sine and the cosine, dependent on the angle you're at along the circle. So to give example, so here is your distance A and your distance B on the circle. You can describe this with a certain angle, which is always defined from the x-axis going counterclockwise. So in this way, we can represent what these functions mean, although the sine, the cosine, and the tangent, you don't actually have to know how to, you can't calculate them particularly easily. If we have a lot of time at the end, I might go into very briefly how you can calculate them by hand, but generally you look at a lookup table for them because they aren't, there isn't like a closed form solution to them, although they do have a specific definition. So with that, I'm gonna give just a very brief overview of how to represent each of these on the unit circle. So for the sine of any angle, so this angle we've chosen here, is just equal to the y coordinate, in this case is b. Technically, if you guys remember your Pythagorean theorem, this is the adjacent, this is the opposite, and this is the hypotenuse. It's actually b over the hypotenuse, but in this case, that's 1, so it's just b for now. Similarly, the cosine is defined as the x coordinate on this unit circle for the same angle. And with the same logic, you should have it's the opposite over the hypotenuse, but the hypotenuse is again 1. Finally, we have our tangent, which is just defined as b, or as our y coordinate over our x coordinate. And this, again, these are all just definitional. This is just a function you can plug into your calculator, and you shouldn't be too concerned with trying to logic your way through how you can get to an actual number, although there are approximation methods you can use for that. This is just a well-defined function that behaves in a certain manner. So here is an example of what this unit circle looks like with all of the values for pi over 6, pi over 4, pi over 3, and pi over 2, and then multiples thereof. So again, this is our cosine, and this is our sine. So our x and y coordinates. And you can use a lookup table like this for all of the problems you might be doing. There are also old style, like kind of before they had calculators, they had these things called slide rules that would allow you to calculate more angles that aren't included on a unit circle like this. And then I wanted to give a just quick demonstration of what these sines and cosines look like when you plot them. Like a lot of times you will see them plotted as cosine of x, where x is like some variable rather than just a static angle. So you can see that this is centered around 0. So you can see that when you are at 0, your sine is at 0, but your cosine is at 1. And that makes sense because if you're at 0 angle on a circle, you're right here, which is the absolute max in x, but 0 in y. Okay, so now with that, I want to do a couple example problems of this. And we're kind of giving you the answer almost, or like 2 options for the answer. So here we want to calculate first the sine of 30 degrees. And we've given you this unit circle with that location marked. So if you guys could put in the chat what you think the value of sine at 30 degrees is. Got a lot of very good answers. Yes, it's just your y coordinate. Whenever you're looking at a unit circle representation, just take the second value, and that is always going to be your sine. So sine of 30 degrees is 1/2. I don't remember. Do I have just sine? No, I have all of them. Okay, I'm not going to go there. Okay, next we have our cosine, which similarly we can just read directly off the unit circle. Can anyone tell me what that is? There's only one other option marked, so it should be pretty straightforward. Yes, thank you everyone for putting your answers in the chat. Yuritsa and Dristy and Russell. Yeah, these are all, you're all correct. It's just square root of 3/2. You can see right here, that's our cos. This is our sine. Now we have one, it's a little trickier, our tangent of 30 degrees. So if you remember, this is equal to one of these values over the other. Yes, I'm getting a lot of correct answers. I don't think I've gotten a single wrong answer yet. This is just equal to 1 over square root of 3, or if you want to make it like rational, I don't actually know. If you want to make it over a whole number, you put square root of 3/3, and that's equivalent. So here's the official answers. And these ones are represented in radians. The trick for radians is that, I guess, 1 radian is equal to, or wait, let's not do that way. To convert between radians and degrees, you can do your number in degrees, so 30 degrees here, divided by 180 degrees, which is equivalent to pi, and multiply it by pi. And so that is how you get this pi over 6. So to convert from radians to degrees, you just take any, you can do the exact opposite. So I'll just do, I guess, pi radians is equal to 180 degrees. And that is very easily just how you convert between the two. Okay, so that, I think we have a couple more examples we'll go through. We can speed these a little bit. Actually, I'm going to do a poll, not a real poll because I don't know how to set one up, but how has this been so far? Do you guys understand trigonometry, or are you a little confused? Because we can go a little slower or a little faster. And if you're not sure what's going on, please do say, no, I don't understand, in the chat. I will not be, I will slow down for people. But okay, if you guys think it makes sense, then we'll kind of blast through things a little bit more. Okay, so here I'm going to write out all 3, and I want you guys, you can see we're now looking at pi, or 4 pi over 3 radians, or 240 degrees. You can see we've written the right location on this unit circle already. So just send to the chat what you think each of these values is. What is the sine of 4 pi over 3? Nice. Thank you from Audrey, Aiden, Russell, Emma. Thank you, everyone. Yep, you're right. It's all just this y coordinate. That's our sine. It's negative square root of 3/2. Similarly, what's our cosine? Only 2 options. Great. Okay. Everyone's got it yet again. It's just 1/2. Now for the tangent, can you guys do division? Nice. Okay, yes, everyone that has sent, you are correct. or yeah, you are correct. It's just square root of 3. Okay, so just kind of blasted through that. Do you guys have any questions on the content so far? If not, we're going to move on to coordinate systems. It sounded like you guys understood these pretty well, and going through quickly, everyone seemed to get it.
Sarah, can you maybe just give us a preview of why we're reminding ourselves of sine, cosine, tangent, and like its connection to future quantum computing concepts?
Oh, sure. So one thing that we're going to be using a lot later on in this course is the Bloch sphere. It's named after a German guy named Bloch. That's why it has a funny name. But it's a sphere, which is actually in 3D space, not in 2D space, but we will go into more 3D space later, where we can take this as y, this as x, and this as z. You may have seen this in your classes so far, but if you point straight up on the Bloch sphere, this corresponds to the quantum state 0. If you point straight down, it corresponds to the quantum state 1. And then within this xy plane, which is kind of where we've been dealing with so far, this is the phase of your quantum state, which can be pointing in any direction. And your phase is very well defined for a perfect superposition state. So anything that's directly along these two, this axis is the 0 plus the 1 state, which is then normalized by this square root. And so whenever you're looking at what phase you have along this plane, if you're trying to find out where you are along this plane, then you can actually do that with these same trigonometric tricks. So the phase that you normally see on these terms, typically it's attached, let me move this over a little bit. Oop, oh no. Typically it's attached to your 1 cut, and your phase is here. And this could be like a pi over 6 angle. And if you guys need to find out where on this xy plane pi over 6 is, and like what values that actually is, you can do it the same way as we've been doing for all these trigonometric functions thus far. So I've gotten a question about, so x and y are just the relative, the relative phase of your quantum state. So it's a bit hard to describe, but you can, the unique thing about quantum systems is that you have a well-defined phase. So in what we see in life, we don't see these phases at all, so we don't think about them. But they always appear as this kind of exponential term. This is a theta, it's an angle. They always appear as these kind of exponential terms. But when we have a lot of particles acting together, when you add up all these phases and they're all randomized, they all average out to 1. So you don't see them at all. Or I guess to 0. They average out, so you don't see any impact of them. Meanwhile, in a quantum system, we have very well-defined phases for each state. And so it's just an extra value that you have to use to describe what your state is. Yeah, we will be going into polar coordinate systems and transforming from Cartesian to polar coordinates just in a moment. Sorry, the phase is only on the 1 cut. It's a relative phase. If you multiply your entire system by that phase, then that has a different meaning. Yeah, so typically we take the phase of 0 to be like 0. but that's an arbitrary definition. The whole point is that you just have some relative phase between your states. Yeah, so Benjamin, that is correct. Yeah, you can define what mixing of your 0 and 1 state you have, and then the phase you have. And so the mixing of your 0 and 1 state, oh, this is disconnected. Let me try to make that reconnect. One sec, sorry guys. Okay, sorry for the delay. Sometimes things just disconnect at random. Okay, there we are. Okay, so what we'll see when we go into polar coordinates is we have what we can describe as the, I guess, mixing between the two states can be taken as your R in polar coordinates, or can be mapped directly to your R, and then your phase can be taken as just your theta. Okay, so with that, I think we can move on to the next section just for the sake of time. I'm gonna go into coordinate systems. So here we have a point. We don't know where that point is yet, or we don't have a way of describing the point because we haven't developed a coordinate system to describe to others where this is. All they can say is there is a point somewhere on the screen, which is good, but not sufficient when trying to communicate to others or translate where this point is. So what we do is we put a coordinate system here where this is just a Cartesian coordinate system. You can take this is X, this is Y. So this point would then be 4X, 3Y. Although we could have just as easily incremented all these values by 1 and shifted over this entire image. And then it would be 3X, 3Y. It's really very general where we put it if we have the absolute freedom to place a single point. So now if we go back to that dot and we don't want this 4, 3 location, we could choose to do a rotation even to describe this. So now we're in a completely different system where this is instead 5, 0. And so this is a really kind of intuitive way to think of choosing a coordinate system in which to measure something. You can transform between these coordinate systems through shifting or rotating the coordinates, which you can describe mathematically, but that's a little bit more complicated, and computers are very good at doing that. So we don't have to anymore. So one coordinate system that I kind of hinted at a little bit earlier that is very important to be able to understand is the polar coordinate system, where instead of describing things with regard to the X and the Y, like we had before, I'm gonna get rid of those, we're instead going to use the distance from 0 to whatever point, which we'll call R, and then the angle from the x-axis, which we'll call theta. And so this is very analogous to the trigonometric functions we used earlier. So I guess this is just writing out what I already wrote out. I don't really like slides very much. I like writing, if you haven't noticed. So this is still 4, 3 in Cartesian coordinates. But if we want to convert them to polar coordinates, we can do that, just written out here. But the conversion is taking R is equal to x squared plus y squared, which if you remember this from previous courses, this is the Pythagorean, if I'll spell this right, theorem. It's the same idea as with a triangle. If you take the long side to be R this to be x and y. Pythagoras just said that r squared is equal to x squared plus y squared. We've known about this for a couple thousand years. Just to get directly to r, we just take the square root of the whole thing. So that's how we get this equation. Next is the angle, which we can take a variety of different ways, but the most common, like I guess general one, is just to take the tangent of our y coordinate over our x coordinate, which again, and that just will give us the angle, which we've defined it this way, or the inverse tangent of the y coordinate over our x coordinate. And so with this, we can easily convert between the two. And so now if we go back up to here, let's just do that conversion. So we want our r to be equal to the square root of 4 squared plus 3 squared. So that's, I guess, 16 plus 9 is 25. So that just gives us 5 for our r. The theta is a little bit more complicated. You might have to calculate this in the, like with the calculator, but this is the inverse tangent. So this is doing the opposite of what tangent, or of the tangent that we learned earlier. So this 3 over 4 is actually the value you would get out by taking the tangent of whatever this angle is. And you can see that like this I don't know off the top of my head. You can easily look this up. Yeah, I've gotten a very good question from Abhijit Shreyas. I don't know if I've said your name right. Sorry if I haven't. We can define this angle as the inverse of any of the other trigonometric functions as well. The tangent, I guess, is just a little bit more generalized and isn't as sign sensitive. So it is just a convention. Yeah, generally we do operate in radians because like most computers by default operate in radians, or when they do this math, but it is an equivalent representation. It doesn't matter too much which one you choose. But as far as the problem sets go, I believe everything should be in radians. Okay, so with that, we can do a similar thing to convert from polar to Cartesian coordinates, where now instead of doing the prior conversion, we can do a trigonometric function to get each of these, which is this exact same thing that we did at the beginning of the course when we were discussing trigonometry. So our x coordinate is just what we'd expect from the unit circle of just the cosine of the angle, while the y is the sine of the angle. This r is the only difference, and that is because our circle is no longer necessarily a unit in radius. So if r is equal to 1, then this r just goes away because it's 1 times anything is just whatever you're multiplying it by. But if we take this radius to now be 5, we just have to multiply everything through by 5. So this angle up here, or this y value, I guess, could be 5 sine of, let's say, 30 degrees. Yeah. So that's the only difference. Other than that, everything on these unit circles carries over, and you can still use them as lookup tables for the sake of these conversions, but you can also put it into your calculator. So here we have an example of converting from polar coordinates to Cartesian coordinates. So we've given you an R and a angle. I think I put a unit circle right below. So if you guys want to look up, we want R equals 1, theta equals pi over 3. Can you guys calculate what our x and our y would be? And to remind you, x is our, oh, not sine, sorry for the mistake there, our cosine theta, and y is our sine theta. Oh, is it frozen? Oh no. Let me stop sharing and reconnect. Sorry that we're having so many technical issues tonight. I have not had this problem in previous labs. Okay, sorry, here is our unit circle. And I want you guys to calculate what the x and y would be for these coordinates I've put in. Great. So I've given you all the information you need. I'm gonna give you a minute or two to calculate this. Nice. I've gotten some very good responses in the chat. Thank you, Xavier and Michael and Magana, and Farhan and Archie. You guys are all right. What we want to do is we want to look for the angle we've chosen, which is this one right here. And then our radius is just 1 because we're on a unit circle, or because we've chosen it to be, but we don't have to do anything beyond just looking at this right point on the unit circle. So we want this line here, and that gives us an x equals cosine theta equals 1/2. I guess that's not really a logical way to write it out, but then sine theta is equal to y is equal to square root of 3 over 2. So this is a really easy way to just do the conversions, just looking at one of these unit circles. Of course, you can also put it into your calculator, but this visualization makes it a little bit more straightforward. We have one more example that I think I'm going to skip in the interest of time, but definitely do it on your own time. It's pretty quick to do the same thing again if we're looking at 2 pi over 3. You just want to look at this line, and then you should find your answers right here. Okay, any questions on these polar coordinate and Cartesian coordinate transformations? And if you have any more in-depth questions, I'll try to leave a little bit of time at the end, but we do have to get through one more topic. Okay, great. Thank you for telling me it was clear. That's good to know. At least someone found it clear. Okay, so I'm gonna go skip this because we're going to do summation notation, which is going to make things a lot easier for representing all of our equations. And I'll give you a little quick way of finding these sines and cosines using the summation notation. So if we have a sum like this, where we're going from 1 to 10, we're just adding all these together, this is a very long way to write it out. Like I have all these 10 items here. This is ridiculous. It takes up too much space. If I wanted to add even, if I wanted to go to 100, I could never fit it on a single page. It's just not going to work. So what we do is we add this symbol here, which is a large omega. I believe, no. It's that symbol, sigma, thank you. A large sigma that we sum from whatever number we put inside it, which in this case is I. We can take what the starting point is, which here we take it to 1, and then we sum all the way to 10. So in this way, we go, this just says that we do 1 plus 2 plus 3 plus 4 all the way up to 10. If we modified this so that instead maybe it was I times 2, which isn't super informative, it would instead be 2 plus 4 plus 6 plus 8, like all the way through. And then this makes it a lot more condensed to represent anything we might want to show. So here's another way we can represent it, where instead we have a function of some kind or a variable of some kind that has a subscript. So if we could define this subscript to mean just about anything, if we said a sub 1 equals 4, a sub 2 equals 20, etc., then this would just sum over all these a's. And this is often used for like vector notation, which we'll get into a little bit more later on in the course. But this is also very useful for how computer science, or when you're doing computer programming, you might want to have a variable with many entries, and then this little subscript can be used as an index to perform all of these form sums or any kind of operation on these variables. So I want to give this is concept of a Taylor expansion, which uses this exact concept we just went over, these sums. I'm going to actually go to this page because there's a little bit more space. So what we want to do for a Taylor expansion, let me write that out, is we want to approximate some of these functions that we can't easily calculate by hand. So these are just defined, someone came up with these, Taylor came up with these at some point. I guess you can't really like come across this analytically, it's just a definition. But to represent sine of x, I'm just going to do 1 for the sake of time. We can actually use this summation notation, or actually I'm going to write it out first, just so it's maybe a little bit more intuitive. We can do the value x minus x to the 3 over 3 exclamation point, where this exclamation point, like 3 exclamation point means 3 times, let me fix that, sorry guys, times 2 times 1. This exclamation point just means that you multiply the number times every number decrementing down to 1, or it's called a factorial. And then you add the next term to the 5th, and this goes, the sign always reverses direction, and this goes to infinity. So the way you can represent this with this summation notation, and this is a little bit more advanced, so no worries if you don't totally follow. This is just a way, if you are confused about sines and cosines and you don't like that you can't just like calculate them, because I hated that when I was in high school. Like, I thought that was just awful. I hated that I had to put it into a calculator. I much preferred doing Taylor expansions. So to represent this, you can do this as a sum over n, starting from 0, going to infinity, of -1 raised to the n times x to the 2n minus 1 over 2, or should it be plus 1? 2n plus 1. Yeah, 2n plus 1 plus 1 factorial. And this will create the same series as this. And so to first order, you can very easily do these Taylor expansions to calculate the sines and cosines. And you want to make sure this is always in radians. So this is a really quick overview. No worries if you don't totally understand it. I'm going to very quickly do the post-lab Zoom feedback, if we can open that poll. Again, no worries if you don't totally understand the Taylor extension, and then I'll take questions while we're at it, since we have a couple minutes left. And I'll go back to the Taylor expansions. I think it's a very like direct use of summation notation that will prove very useful if you ever want that. The proof for this is pretty complicated, so you should definitely look it up on your own time on Wikipedia, but you can, or it's actually not that complicated. You can go from like the definition of an exponential to the definition of a sine and a cosine. Okay, so I've got a very interesting question from Arsh about how electron holes are formed or created. So a hole isn't a real particle. I guess, it's generally defined as just the absence of an electron, but describing it, the way that people have found of describing charge transport in these transistors is that it often, you can't really describe it very accurately by saying the electrons move. You have to describe it as the holes moving, even though they technically don't exist. They're just the absence of the electrons. But it's mostly just a sign convention because a current is defined as moving in the opposite direction to the electron motion. So a hole current is instead like, I guess, yeah, hole current is in the opposite direction to the hole motion or the same direction as the electron motion. So that's just a very general overview. Okay. So we're right at 9 p.m. I can answer a few more questions if anyone wants to stay on. I know we went into like a lot of depth at the very end, but we're at the end of the class. So thank you everyone for showing up. If you need to go, please feel free to log off now. And thanks again for attending lab.
Thank you.
Bye.
Thank you.
Bye. Thank you. Thank you. Bye.
Thank you.
So I've gotten another question from Arsh about MOSFET. So a transistor is kind of, a transistor is kind of innately a mini particle device. There is a thing called a single electron transistor, which is very, very closely related to a superconducting qubit, or certain types of superconducting qubits, where you have a superconducting island. So I can just draw it like this. It's a bit weird. So you might have like a little lead, and then you have an island here that is capacitively coupled. There's like a very small gap here. And these are all superconducting. In a superconductor case, this kind of goes to like something else. And in a single electron transistor, the number of electrons sitting here, or the number of Cooper pairs sitting here, which are just 2 electrons, is the value for the potential on the transistor. So you can make kind of more quantum transistors that work in a very similar way to a real transistor, but they're not by themselves a quantum logic device, or they're not generally used as a quantum logic device. Okay, so I've got a question from Kevin. I was an electrical engineering major for quantum, and yes, I remain an electrical engineering major. I actually specialize in electrical engineering and computer science at MIT. Okay, I'll answer like 2 more questions and then oh, so if you guys want to see this, the similar Taylor expansion for a cosine, which I would have liked to be able to get to all of it because I know I kind of rushed through it, but I think it's so like useful. I don't know, I did not understand cosines or sines at all when I just thought they were awful. Like I made up my own like expansion that was not quite the Taylor expansion. It wasn't quite right, but it was close enough that I could generally get the answer to like a couple decimals. For a cosine, you can use the same kind of idea of just like adding and subtracting terms. I'll just show it in summation notation where it still goes to infinity. Got -1 to the n x of 2n over 2n factorial. And this will give you your cosine. You can kind of see it intuitively that the sine will be at 0 when x is 0. And then the cosine, the first term is a 1, and then you have your x squared over 2 factorial plus x to the 4th over 4 factorial. And so this will be at 1 when x equals 0. Okay, so we're at 9:05. Thank you everyone for coming. I think I'll call it a day for this class, but hopefully this was very helpful for all of you, and hopefully I didn't stress you out too much with the Taylor expansions. I just think that it is a different way of looking at them and a different way of thinking about these calculations that I think is more intuitive, as it is kind of on some level just a predefined function that behaves in a certain manner. Yeah, okay. Thanks everyone. Bye.
Thank you.
Thank you. See you next week.
Thank you.
Thank you.
Bye.